Hello there, and welcome. Tonight I want to take you somewhere quiet, somewhere between the familiar weight of your own body and the vast, invisible architecture of forces that surrounds us all. I want you to feel, just for a moment, the gentle pressure of your back against the bed, or perhaps the soft support of a chair, or maybe you're lying on a couch, feeling the subtle way gravity holds you there, not demanding, not harsh, just present. Always present. And as you settle into this awareness, as you let yourself really feel that downward pull that has been with you since the moment you were born, I want to invite you into a question that might seem simple at first, but the deeper we go, the more it begins to whisper about something profound, something that touches the very nature of reality itself. You know, right now, as you're listening to me, there are invisible fields passing through your body. Electric fields from the wiring in your walls, magnetic fields from the earth itself, radio waves carrying signals to phones and computers, all of these invisible rivers of force flowing through you, around you. Some of them you can block, some you can shield yourself from. And yet, there's one force, one field that you can never escape, never shield yourself from no matter what you do. Gravity. That gentle, persistent pull that keeps you connected to this planet, that shapes the arc of every ball you've ever thrown, that determines the rhythm of the tides and the orbit of the moon. And here's where our journey begins tonight, in this curious asymmetry, this strange difference between forces that seem, at first glance, like they should behave the same way. But before we drift deeper into this mystery, I'd love to know where you are in the world right now. Are you in a bustling city where the lights never quite go out? Or perhaps in a quiet suburb where the stars peek through when the clouds part? Maybe you're in the countryside where the night is truly dark and the Milky Way spreads across the sky like spilled milk. What time is it where you are? Is it that deep part of the night when the world feels hushed and still? Or perhaps early evening when you're winding down from the day? Wherever you are, whenever you're listening, you're part of this exploration we're taking together. And if you find yourself enjoying this gentle journey through the mysteries of physics, if you find that these quiet contemplations help you drift off to sleep while still feeding that curious part of your mind, I'd be so grateful if you'd consider subscribing or following along for more of these nighttime wanderings through the universe. There's something beautiful about knowing that all around the world, at different times, in different places, people are lying down, looking up at the same questions, feeling the same forces, wondering about the same mysteries. Now let me paint you a picture. Imagine you're holding your phone right now, or maybe it's charging on a nightstand nearby. Inside that device, billions of electrons are dancing, flowing through circuits, creating electric fields that carry information, that light up pixels, that connect you to the vast network of human communication. And here's something remarkable. If you were to wrap that phone completely in aluminum foil, really seal it up tight, those electric fields would be trapped. The signals trying to reach it would be blocked. The electric fields would hit that metal barrier and stop, unable to penetrate inside. We call this a Faraday cage, named after Michael Faraday, who discovered this principle almost 200 years ago, and it's something we use every day without thinking about it. The metal body of your car protects you from lightning strikes. The mesh on your microwave door keeps the radiation inside from escaping. Elevators, despite being metal boxes, often have trouble getting cell phone signals through their walls. But now, try this thought experiment with me. Imagine trying to build a similar cage for gravity. Imagine trying to construct some kind of box, some kind of shield that would make you weightless inside, that would block the Earth's gravitational pull the way aluminum foil blocks electric fields. You could use any material you want: lead, gold, some exotic space-age composite, even materials that don't exist yet. And what would happen? Nothing. Absolutely nothing. You would still feel your full weight. The Earth's gravity would pass through your shield as if it wasn't even there, reaching through to pull on every atom of your body with the same gentle, inexorable force. This difference, this fundamental asymmetry between electric fields that can be blocked and gravitational fields that cannot, it opens a doorway into understanding something deep about the nature of our universe. It whispers to us about the difference between electric charge, which comes in positive and negative varieties that can cancel each other out, and mass, which as far as we know, only comes in one variety, the kind that attracts. It speaks to something called Gauss's law, a mathematical principle that describes how field lines spread out through space, how they begin and end, how they flow and cancel and combine. Think about the last time you felt static electricity, maybe when you touched a doorknob after walking across a carpet, or when you pulled apart socks from the dryer and they clung together. That little spark, that tiny jolt, that was electric charge jumping through space, positive and negative charges that had been separated suddenly rushing back together. Your body had become charged, perhaps with extra electrons scraped off the carpet, and when you reached for that doorknob, those charges saw their chance to escape, to neutralize, to find their opposites and cancel out. The electric field between your finger and the doorknob grew stronger and stronger until the air itself couldn't insulate anymore and crack. A tiny lightning bolt connected you to ground. But mass doesn't work this way. There's no negative mass that we've ever discovered, no anti-gravity material that pushes instead of pulls. Every atom in your body, every molecule of air around you, every grain of dust floating in the moonbeam coming through your window, they all have mass, and they all pull on each other, always attracting, never repelling. The Earth pulls on you, and believe it or not, you pull back on the Earth with exactly the same force. It's just that the Earth is so much more massive that it barely notices your pull, while you definitely notice its pull on you. As we lie here together, contemplating these invisible forces, I want you to imagine field lines, like gossamer threads spreading out through space. Picture electric field lines radiating outward from positive charges like the spokes of a wheel, or flowing inward toward negative charges like water down a drain. These lines can be redirected, bent, terminated. When they hit a conductor, the charges in that conductor rearrange themselves, creating their own field lines that exactly cancel out the incoming ones, creating a quiet space inside where no electric field exists. It's like noise-cancelling headphones for electric fields, producing an exact opposite that creates silence. Now picture gravitational field lines, and here's where things get interesting. These lines all flow inward, always inward, toward anything with mass. There are no gravitational field lines flowing outward, no anti-gravity sources sending lines away. Every mass in the universe is like a drain with no corresponding fountain, a place where field lines converge but never diverge. And when these field lines encounter matter, they don't stop. They don't get cancelled. They just keep flowing, right through, as if the matter wasn't even there. The gravitational field lines flowing through your body right now have come from the Earth below, but they don't stop at your skin or your bones. They continue upward, out through your ceiling, through the atmosphere, weakening with distance but never truly ending, extending in principle all the way to the edge of the observable universe. This is why we can't shield ourselves from gravity the way we can from electric fields. To block electric fields, we can use the fact that positive and negative charges exist, that they can move within conductors, that they can arrange themselves to create cancelling fields. But with gravity, we have no such option. Every bit of mass only adds to the gravitational field. There's no negative mass to create cancellation, no way to arrange matter to create a gravity-free zone inside. The mathematics of Gauss's law, when applied to gravity, tells us that the total gravitational field flowing through any closed surface depends only on the total mass inside, and since mass is always positive, the field always points inward, always attracts, never cancels. You might wonder, and it's a beautiful thing to wonder about, whether this is a fundamental truth about the universe or just a limitation of our current understanding. After all, for most of human history, we didn't know that electric and magnetic fields were connected, that they were really two aspects of the same electromagnetic force. We didn't know that matter could be converted into energy, that time could slow down near massive objects, that particles could exist in multiple states simultaneously until observed. Maybe, just maybe, there's some exotic form of matter we haven't discovered yet, some way to manipulate gravity that we haven't imagined. Scientists have looked, oh how they've looked, for any hint of negative mass, any sign of gravitational shielding, any crack in the seemingly absolute rule that mass always attracts. In laboratories around the world, in the quiet hours of the night when the building is still and vibrations are minimized, incredibly sensitive experiments search for any deviation from our understanding of gravity. Torsion balances more sensitive than Cavendish could have dreamed of measure the gravitational attraction between small masses, looking for any sign that certain materials might shield this force. Particle physicists search for exotic particles that might have negative gravitational mass. Cosmologists study the expansion of the universe, looking for signs of dark energy that seems to push space apart, wondering if this might be related to some kind of anti-gravity, though all evidence suggests it's something different, something even stranger. And yet, through all of these searches, all of these experiments, gravity remains stubbornly consistent. It follows the rules we've discovered, the patterns we've mapped out. Every mass attracts every other mass. The force decreases with the square of the distance, and nothing, absolutely nothing we've found can block it. This isn't a failing or a disappointment. It's a deep truth about the nature of our universe, a fundamental asymmetry that shapes everything from the formation of galaxies to the way you feel right now, pressed gently against whatever surface is supporting you. There's something profoundly comforting about this consistency, this reliability of gravity. While electric fields flicker and change, while magnetic fields reverse and fluctuate, gravity just continues its patient work, holding everything together. The same force that keeps your feet on the ground keeps the moon in orbit around Earth, keeps Earth in orbit around the sun, keeps the sun in orbit around the center of our galaxy. It's a force that connects you to everything else in the universe, a force that reminds us that we're not separate from the cosmos, but woven into it, part of the same grand tapestry of matter and energy, space and time. As you lie there, feeling your weight, feeling the Earth's embrace, I want you to appreciate what a remarkable thing this is. You're experiencing one of the 4 fundamental forces of nature, the one that shapes the large-scale structure of the universe, the one that Einstein revealed isn't really a force at all, but the curvature of space-time itself. Every atom in your body is following the curves of space that the Earth's mass creates, sliding down the gentle slope toward the center of our planet, held back only by the electromagnetic forces in the ground or bed beneath you that prevent you from falling through. And here's where our contemplation takes an interesting turn. In Einstein's general relativity, gravity isn't something that reaches out through space to pull on you. Instead, mass curves space and time, and you follow the straightest possible path through that curved space-time. It's like rolling a marble on a stretched rubber sheet that has a bowling ball pressing down in the middle. The marble curves toward the bowling ball not because of some invisible string pulling it, but because the surface itself is curved. This is why gravitational fields can't be shielded in the conventional sense. You can't block the curvature of space-time any more than you can block the shape of a hill. You're not being pulled by gravity, you're following the geometry of the universe itself. This geometric understanding of gravity makes the impossibility of shielding even more profound. With electric fields, we're dealing with forces that propagate through space, that can be intercepted and cancelled. But with gravity, we're dealing with the shape of space itself. How do you shield yourself from geometry? How do you block the curvature of the universe? It would be like trying to create a flat spot on a curved surface without changing the surface itself. A logical impossibility, a contradiction in terms. Yet there is one way, and only one way, to not feel gravity, and it's both simpler and stranger than any shield. You fall. When you're in free fall, when you and everything around you are following the same curved path through space-time, gravity seems to disappear. Astronauts in the International Space Station, orbiting Earth every 90 minutes, feel weightless, not because they're beyond Earth's gravity. They're still experiencing about 90% of the gravitational force we feel on the surface, but because they and their spacecraft are falling together, following the same orbital path, with nothing pushing up against them to create the sensation of weight. This is the closest thing we have to a gravity shield, and it's not really a shield at all. It's more like moving with the current instead of against it, flowing with the curvature of space-time instead of trying to resist it. And even this apparent escape from gravity is an illusion. The astronauts are still very much under gravity's influence, still following the paths that mass has carved through. Space-time, they've just found a way to fall that doesn't involve hitting the ground, a continuous fall around the Earth rather than toward it. As we continue our journey tonight through this question of why we can shield electric fields but not gravitational ones, I want you to hold on to this image. You, lying there, connected to everything in the universe through invisible threads of gravitational influence that nothing can block. The moon pulls on you right now, creating tides not just in the ocean, but in your body, though the effect is too small to notice. The sun pulls on you, and Jupiter, and every star you can see, and countless ones you can't. Their influences are tiny, overwhelmed by the Earth's proximity, but they're there, reaching through walls and shields and the entire bulk of our planet to touch you, to include you in the cosmic dance of matter and energy. This is the universe we live in, a universe where some forces can be hidden from but others cannot, where some fields respect boundaries while others ignore them completely. And as we prepare to go deeper into this mystery, to explore the mathematics and experiments that reveal these truths, to contemplate what it means for our understanding of reality, I want you to rest in the knowledge that you're held gently but firmly by forces that have been operating since the beginning of time, forces that will continue long after we're gone, forces that connect you to everything else that exists. The question we're exploring tonight, why can't you shield yourself from gravity but you can from electric fields? It's not just a physics puzzle or a quirk of nature. It's a window into the fundamental structure of reality, a glimpse of the deep rules that govern everything from subatomic particles to galaxy clusters. And as we drift through this exploration together, letting the ideas wash over us like gentle waves, we're not trying to master these concepts or memorize equations. We're simply appreciating the profound beauty of a universe that has such interesting asymmetries, such elegant mathematical structures, such reliable and yet mysterious behaviors. So as you settle in for this journey, as you let your breathing slow and deepen, as you feel the constant comforting pull of gravity holding you safe and secure, remember that you're not just learning about physics, you're contemplating your place in the cosmos, your connection to everything else that exists, your participation in the grand patterns that shape reality. And there's something deeply soothing about recognizing that you don't have to do anything to be part of this. You don't have to understand every detail or grasp every concept. You simply have to exist, to have mass, to be made of atoms, and you're automatically included in the gravitational network that binds the universe together. The gentle pull you feel right now, that subtle pressure of your body against whatever's supporting you, that's your membership card. In the cosmic club, you're proof that you belong here, that you're part of the same physical reality as stars and planets, galaxies and black holes. You can shield yourself from radio waves, from electric fields, from light itself if you close your eyes, but you cannot shield yourself from gravity because gravity is, in a very real sense, the universe's way of acknowledging that you exist, that you matter, that you're part of the whole. And with that thought, that recognition of your unbreakable connection to everything else, we're ready to begin exploring the deeper mysteries of fields and forces, charges and masses, the mathematical poetry of Gauss's law, and the experimental evidence that reveal these truths. But we'll do it slowly, gently, with plenty of time to contemplate and wonder, to let the ideas sink in not through effort but through a kind of intellectual osmosis, the way understanding sometimes comes not when we're trying hard but when we're relaxed, open, receptive to the universe's quiet lessons. Now, as we drift deeper into this mystery, I want to invite you to see something that usually remains invisible, something that surrounds us always but that we rarely think about. Picture, if you will, the space around you, not as empty air, but as filled with invisible lines, flowing and curving, spreading out like the most delicate spider's silk, like streams of water flowing through three-dimensional space, except these streams can pass through solid matter as easily as light passes through glass. These are field lines, the imaginary threads that physicists use to visualize the invisible forces that shape our world, and tonight they're going to help us understand why electric fields behave so differently from gravitational ones. Let's start with something familiar, something you might have played with as a child or seen in a science class. Imagine a simple bar magnet, the kind with a north pole and a south pole, and around it, iron filings sprinkled on a piece of paper. You've probably seen this demonstration, the way the filings arrange themselves into curved lines, flowing out from one pole and curving back to enter the other pole, creating beautiful patterns that look almost organic, almost alive. Those iron filings are showing us something real, something that exists in the space around the magnet even when the filings aren't there. They're revealing the magnetic field lines, the invisible architecture of magnetic force that extends through space. Now, magnetic fields and electric fields are intimately connected. They're really two aspects of the same electromagnetic force. But for tonight, let's focus on electric fields, because they provide such a perfect contrast to gravitational fields. Picture a single electron, just one, floating in the vastness of space. From this tiny particle, electric field lines radiate outward in all directions, spreading through space like light from a star. These lines extend infinitely outward, getting weaker with distance but never truly ending, always pointing away from the negative charge of the electron. The electron sits at the center of its own electric universe, pushing against any other negative charges that might approach, pulling on any positive charges that venture near. Now picture a proton, with its positive charge, also alone in space. From the proton, electric field lines also radiate outward in all directions, but there's a crucial difference in how we think about them. While the electron's field lines point outward, showing the direction of force on a positive test charge, which would be pushed away from the electron, the proton's field lines also point outward, but now they show that a positive test charge would be pushed away while a negative charge would be pulled in. It's a subtle but important distinction that will matter as we go deeper into our exploration. What happens when we bring these two particles near each other? Something beautiful. The field lines from the electron and the field lines from the proton begin to connect, to merge. Lines that were radiating outward from the proton curve through space to terminate on the electron. The separate field patterns of the two particles blend into a single pattern, a unified field that shows the combined influence of both charges. And here's the crucial point. Some of the field lines cancel out. Where the electron's influence and the proton's influence overlap, they can neutralize each other, creating regions where the electric field is weaker than either particle would create alone. This is the beginning of understanding why we can shield ourselves from electric fields. Because electric charge comes in two varieties, positive and negative, and because these charges create fields that can cancel each other out, we can arrange charges to create regions of space where the electric field is zero, or at least very weak. It's like having both hot and cold water taps. By mixing them in the right proportions, you can create water of any temperature you want, including perfectly neutral, neither hot nor cold. Let me paint you a more detailed picture of how this cancellation works. Imagine you're inside a hollow metal sphere, a conductor like copper or aluminum. Outside this sphere, there's a strong electric field, perhaps from a charged object or a thunderstorm. The electric field lines are flowing through space, ready to exert forces on any charges they encounter. But when these field lines reach your metal sphere, something remarkable happens. The free electrons in the metal, and metals have lots of free electrons that can move around easily, feel the force of the external field and begin to move. They redistribute themselves on the surface of the sphere, accumulating on one side and leaving a deficit on the other. This redistribution continues until the electrons have arranged themselves in exactly the right pattern to create their own electric field that perfectly cancels the external field inside the sphere. It's not that the external field has been blocked like light blocked by an opaque object. Instead, the charges in the conductor have created an equal and opposite field that adds to the external field to produce zero field inside. It's like noise-cancelling headphones that produce sound waves that exactly cancel the incoming noise, creating silence through addition rather than blocking. This is a Faraday cage, and it's one of the most elegant phenomena in electromagnetism. The conductor doesn't have to be a solid sphere. A mesh or cage works just as well as long as the holes are small compared to the wavelength of the electromagnetic radiation you're trying to block. This is why your microwave has that metal mesh on the door with tiny holes. The microwaves inside, with wavelengths of about 12 centimeters, can't fit through the small holes, while visible light, with wavelengths thousands of times smaller, passes through easily so you can see your food cooking. Now, you might think, if we can do this with electric fields, why not with gravitational fields? Why can't we build a gravitational Faraday cage? To understand why, we need to look more carefully at what makes electric fields special and what makes gravitational fields different. The key lies in the nature of the sources of these fields, electric charge versus mass. Electric charge is bipolar. It comes in positive and negative varieties that are exactly opposite to each other. An electron and a proton have exactly the same magnitude of charge, just with opposite signs. When you bring them together, their charges don't just add up, they cancel out. A hydrogen atom, with one proton and one electron, is electrically neutral. It creates no electric field at a distance, because the field lines that would emanate from the proton are exactly balanced by the field lines that would terminate on the electron. This is why most matter is electrically neutral. Atoms naturally have equal numbers of protons and electrons, their charges cancelling out perfectly. But mass is different. Fundamentally different. As far as we know, and scientists have looked very carefully, mass only comes in one variety. There's no negative mass, no antimass in the gravitational sense. When you bring two masses together, their gravitational fields don't cancel, they add. Always add. Every atom in your body, every molecule of air around you, every speck of dust floating in the sunbeam coming through your window, they all have positive mass and they all create gravitational fields that point inward, that attract rather than repel. Picture the gravitational field lines around Earth. They all point inward, converging toward the centre of our planet like billions of arrows all pointing to the same target. There are no gravitational field lines pointing outward, no anti-gravity regions where mass pushes things away. The Moon's gravitational field, also all inward-pointing lines. The Sun's field? Inward. Every star, every planet, every asteroid, every grain of cosmic dust, they all create fields with lines that point inward, that pull rather than push. This is why we can't create a gravitational Faraday cage. To cancel a gravitational field, we would need negative mass, anti-gravity matter, that creates outward-pointing field lines. We would need to be able to arrange positive and negative masses in such a way that their fields cancel out in some region of space. But we don't have negative mass. We've never seen it, never created it, never found any evidence that it exists, and without it, we can't cancel gravitational fields the way we can cancel electric fields. The mathematics of this is encoded in something called Gauss's Law, one of the most beautiful and powerful principles in physics. Gauss's Law tells us about the relationship between field lines and their sources. For electric fields, Gauss's Law says that the total electric field flowing through any closed surface depends on the net charge inside that surface. If you have equal amounts of positive and negative charge inside, the net charge is zero, and no net field lines flow through the surface. The field lines that start on positive charges end on negative charges, all contained within the surface, with no net flow outward. But for gravitational fields, Gauss's law takes a different form. The total gravitational field flowing through a closed surface depends on the total mass inside, and since all mass is positive, the field always flows inward. There's no cancellation possible, no way to arrange masses to create zero net field. Every bit of mass contributes to the inward flow of field lines, and they all add up, never subtracting, never cancelling. Think about what this means for the space around you right now. Electric fields from various sources, power lines, electronic devices, radio transmitters are flowing through your room, but many of them are being blocked or redirected by conductors. The metal in your walls, the electronics in your devices, even your own body to some extent, all of these are reshaping the electric field patterns, creating shadows and quiet zones where fields are weak or absent. Your room is a complex landscape of electric fields, constantly changing as devices turn on and off, as charges move and redistribute. But the gravitational field in your room is much simpler and much more persistent. It's dominated by Earth's gravity, pointing almost straight down, barely affected by the walls, the furniture, or anything else in your room. The gravitational field lines pass through everything as if it weren't there, unchanged, unblocked, unshielded. You could surround yourself with tons of lead, with exotic materials, with the densest substances known to science, and the Earth's gravitational field would still reach through to pull on every atom of your body with exactly the same force. There's something both beautiful and slightly unsettling about this absolute penetration of gravity. It means you can never hide from it, never escape it, never shield yourself from it. But it also means you're always connected to everything else in the universe. The gravitational field lines flowing through you right now connect you to the Earth below, yes, but also to the Moon, the Sun, the planets, the stars. Every mass in the universe contributes to the gravitational field at your location, even if most of those contributions are too small to measure. Let me share with you a way to visualize this that I find particularly moving. Imagine you could see gravitational field lines. Imagine they glowed with a soft blue light. Looking down, you would see lines converging from all directions into the Earth, a vast network of blue threads all pointing toward the centre of our planet. But if you looked carefully, you would also see fainter lines, barely visible, pointing toward the moon when it's overhead, toward the sun during the day, even incredibly faint lines pointing toward distant stars and galaxies. You would see yourself at the intersection of countless field lines from every mass in the universe, a unique point where all these influences converge. Now imagine you could see electric field lines too, glowing perhaps in red. The picture would be completely different. You would see field lines starting and ending on charged objects, creating complex patterns that change constantly. When you turn on a light switch, field lines would suddenly appear, flowing through the wires. When you rub a balloon on your hair, you would see field lines radiating from the balloon, then jumping to other objects as the static discharge occurs. And crucially, you would see dead zones, places where conductors have arranged their charges to create regions with no field, electromagnetic shadows where the red lines don't reach. This difference in behaviour between electric and gravitational fields has profound implications for how we interact with the world. We live in an electromagnetic civilization. Almost all of our technology depends on our ability to control electric and magnetic fields, to channel them, switch them, shield them. Every circuit in every device is essentially a carefully designed pattern of conductors and insulators that guides electric fields and currents exactly where we want them to go and keeps them away from where we don't want them. But we have no such control over gravity. We can't channel it, can't switch it on and off, can't shield it. The best we can do is work with it or against it. Our buildings must be strong enough to support their weight against gravity. Our rockets must be powerful enough to climb out of Earth's gravitational well. Our satellites must be precisely positioned to balance gravitational and centrifugal forces. We are, in a very real sense, at the mercy of gravity in a way that we're not at the mercy of electromagnetic forces, yet there's something elegant about this limitation, this asymmetry between forces we can shield and forces we cannot. It tells us something deep about the structure of the universe, about the fundamental difference between electromagnetic and gravitational interactions. Electromagnetism is in some sense optional. Objects can be charged or neutral, can interact electromagnetically or not. But gravity is mandatory. Everything with mass or energy participates in gravitation. No exceptions, no opt-outs, no shields. This mandatory nature of gravity is what makes it so special in physics. It's why Einstein's general relativity treats gravity not as a force like electromagnetism, but as the curvature of spacetime itself. In this picture, gravitational field lines aren't really lines of force flowing through space, but rather indicators of how space itself is curved by the presence of mass and energy. And you can't shield yourself from the shape of space any more than a two-dimensional being living on a curved surface could shield itself from that curvature. As we continue to explore this difference between electric and gravitational fields, I want you to appreciate the deep beauty of what we're discovering. The universe has given us forces with fundamentally different characters, fundamentally different behaviours. Some forces allow for privacy, for shielding, for selective interaction. Others demand universal participation, connecting everything to everything else whether we like it or not. And in this difference, in this asymmetry, we find not a flaw or a limitation, but a feature that makes the universe more interesting, more complex, more beautiful than it would be if all forces behaved the same way. The field lines we've been imagining, these invisible threads that connect charges and masses throughout space, they're more than just a visualization tool. They represent something real about how the universe organizes itself, how forces propagate through space, how objects separated by vast distances can still influence each other. And the fact that some of these lines can be blocked while others cannot, that some forces respect barriers while others ignore them completely. This tells us that the universe has a kind of depth, a layered structure where different forces operate according to different rules. Right now, as you lie there listening, you're at the center of your own electromagnetic universe, creating field lines that radiate outward from the charges in your body, while simultaneously being at a point in everyone else's gravitational universe, feeling the combined pull of every mass in the cosmos. You're both a source and a receiver, both a creator of fields and subject to them, participating in the grand electromagnetic and gravitational dance that holds atoms together and keeps planets in their orbits. In the gentle hush of a laboratory late at night, when the building has settled and the vibrations of the day have faded away, scientists conduct some of the most delicate experiments ever devised by human minds. These experiments, carried out in the soft glow of instrument panels and the quiet hum of vacuum pumps, have revealed to us the hidden rules that govern electric and gravitational fields. Tonight, I want to take you into these quiet spaces to share with you the patient observations and careful measurements that have shown us why we can shield one force but not the other. Let's begin with Michael Faraday, working in his laboratory at the Royal Institution in London in the 1830s. Faraday was not a mathematician. He thought in pictures and physical intuitions rather than equations. But he had an extraordinary ability to design experiments that revealed the invisible architecture of electromagnetic fields. One of his most famous demonstrations involved what we now call a Faraday cage, though he simply called it an interesting electrical phenomenon. He built a room-sized cube covered with metal foil and had himself closed inside with his most sensitive electrical instruments. Outside, his assistants operated powerful electrostatic generators, creating sparks and electrical discharges that would normally be detected anywhere nearby. But inside his metal cage, Faraday's instruments showed nothing. No electrical effects whatsoever. The metal shell had created a perfectly quiet electrical environment, completely isolated from the electrical storm raging outside. What Faraday had discovered, though he wouldn't have described it in quite these terms, was that the free electrons in the metal conductor had automatically rearranged themselves in response to the external electric field, creating their own field that exactly cancelled the external one inside the cage. It wasn't a matter of blocking the field like a wall block sound, but rather a dynamic response where the conductor actively creates a counterfield. The electrons move until they reach an equilibrium where no electron feels any net force, which only happens when the electric field inside the conductor is zero. This automatic, self-organizing behavior of charges in conductors is what makes electrical shielding possible. But Faraday's genius went beyond just discovering this shielding effect. He realized that this phenomenon revealed something fundamental about electric fields themselves. He introduced the concept of field lines, those imaginary threads we were visualizing earlier, and he understood that these lines must begin and end on charges. In a conductor, the charges can move to wherever they need to be to ensure that field lines don't penetrate the interior. It's as if the charges are smart, automatically arranging themselves to create the exact field pattern needed to maintain zero field inside. Now let's move forward in time to a different kind of experiment, one that tried to find if gravity could be shielded in any way. In the late 1700s, Henry Cavendish performed one of the most delicate experiments in the history of physics. He built what's now called a torsion balance, a horizontal bar suspended by a thin wire with lead spheres at each end. Near these spheres, he placed larger lead weights. The gravitational attraction between the spheres and the weights would cause the bar to rotate slightly, twisting the wire. By measuring this tiny rotation, Cavendish could measure the gravitational force between known masses. The experiment had to be incredibly sensitive. The gravitational force between laboratory-sized objects is almost unimaginably weak. Cavendish had to account for air currents, temperature changes, vibrations from footsteps or carriages passing outside. He built his apparatus in a sealed room and observed it through telescopes from outside to avoid disturbing the delicate measurements. The twisting of the wire was so slight that he had to use a beam of light reflected from a mirror to amplify the motion enough to see it. What Cavendish found was remarkable in its consistency. The gravitational force followed Newton's law perfectly, proportional to the product of the masses, inversely proportional to the square of the distance. But more importantly for our story tonight, he found no evidence that any material could shield or block this force. He tried placing various substances between the masses, metals, insulators, different densities of materials. Nothing made any difference. The gravitational attraction passed through everything as if it weren't there. Modern versions of the Cavendish experiment have become extraordinarily sophisticated. In underground laboratories, shielded from vibrations and temperature fluctuations, scientists use laser interferometry to measure displacements smaller than the width of an atom. They've tested whether certain materials might shield gravity even slightly, whether certain crystal structures or exotic materials might have unusual gravitational properties. The answer has always been the same: gravity cannot be shielded. Every measurement confirms that gravitational fields pass through all known materials without any reduction, without any deflection, without any change whatsoever. Let me share with you one particularly beautiful modern experiment that highlights this difference between electromagnetic and gravitational fields. Scientists created what they call a gravity gradiometer, an instrument so sensitive it can detect the gravitational field of a person walking by in the hallway. The instrument consists of superconducting masses levitated in magnetic fields, their positions monitored with incredible precision. When they surrounded this instrument with tons of lead shielding, enough to block essentially all electromagnetic radiation, the gravitational measurements didn't change at all. The lead blocked gamma rays, X-rays, radio waves, even neutrinos to some extent, but gravity passed through as if the lead weren't there. Now, this is where Gauss's law becomes not just a mathematical abstraction, but a profound statement about the nature of reality. Carl Friedrich Gauss, one of the greatest mathematicians who ever lived, formulated a law that connects the field lines we've been imagining to their sources. For electric fields, Gauss's law says something beautifully simple. The total electric flux through any closed surface, think of flux as the number of field lines passing through the surface, is proportional to the total electric charge enclosed within that surface. Let me make this more concrete. Imagine a soap bubble with an electron inside it. Electric field lines radiate outward from the electron passing through the soap film. Gauss's law tells us that the total number of field lines passing through the bubble's surface depends only on the charge inside. 1 electron's worth of field lines. Now, if we add a proton inside the bubble as well, what happens? The proton has an equal and opposite charge to the electron. Field lines that were radiating outward from the electron now curve back to terminate on the proton. The net flux through the bubble's surface becomes zero. No net field lines exit the bubble because the positive and negative charges cancel each other out. This is the mathematical foundation of why Faraday cages work. When external field lines try to enter a conducting shell, the charges in the conductor rearrange themselves to create an equal and opposite flux, maintaining zero net flux and therefore zero field inside. The mathematics demands it, and nature obeys the mathematics with perfect fidelity. But when we apply Gauss's law to gravity, something different happens. The gravitational version of Gauss's law says that the total gravitational flux through a closed surface is proportional to the total mass enclosed. But here's the crucial difference. Mass is always positive. There's no negative mass to create cancellation. If you have mass inside your imaginary surface, the gravitational field lines all point inward, all contributing in the same direction. You can't arrange masses to create zero net flux because all masses contribute flux in the same direction, inward. Scientists have looked for violations of this principle with extraordinary creativity and persistence. They've searched for materials that might have negative gravitational mass, even though such materials would violate our understanding of energy and momentum conservation. They've looked for exotic particles that might fall up instead of down in a gravitational field. They've even examined whether antimatter might have negative gravitational mass, though all theoretical predictions and recent experiments suggest that antimatter falls down just like regular matter. One of the most precise tests involved dropping ultra-cold neutrons in a gravitational field and watching how they bounced. Neutrons are electrically neutral, so electromagnetic forces don't affect them, making them perfect for studying pure gravitational effects. Scientists created neutrons so cold they moved slower than a walking pace, dropped them in a vacuum chamber, and watched them bounce on a mirror-smooth surface. The bouncing pattern exactly matched what you'd expect from ordinary gravity. No surprises, no anomalies, no hint of any way to shield or modify the gravitational force. Another fascinating series of experiments has tested whether gravity behaves the same for all types of matter. This is called the equivalence principle, and it's been tested to extraordinary precision. Scientists have compared how different materials fall in Earth's gravitational field: aluminum and gold, uranium and copper, even exotic materials like graphene and superconductors. They all fall at exactly the same rate, in a vacuum of course, where air resistance isn't a factor. This universality of gravity, the fact that it affects all matter in exactly the same way regardless of composition, is another reason why gravitational shielding seems impossible. The Eötvös experiments, named after the Hungarian physicist who pioneered them, have pushed this testing to almost absurd levels of precision. Modern versions can detect differences in gravitational acceleration as small as 1 part in a quadrillion. They found that different materials, different elements, different isotopes all experience exactly the same gravitational field. There's no material that gravity affects differently, no substance that could be used to create a gravitational shield or lens or filter. Even in space, satellites have conducted experiments looking for any deviation from our understanding of gravity. The Microscope satellite launched by the European Space Agency contained test masses of different materials in free fall, monitored with incredible precision as they orbited Earth. For 2 years, it watched these masses, looking for any difference in how they responded to Earth's gravity. The result? Perfect agreement with the equivalence principle to within a few parts in 100 trillion. Gravity treats all matter exactly the same. But perhaps the most profound evidence for the unshieldable nature of gravity comes from astronomy. When we observe binary pulsars, pairs of ultra-dense neutron stars orbiting each other, we can measure their orbital decay with extraordinary precision. These systems are losing energy by radiating gravitational waves, ripples in spacetime itself that carry energy away at the speed of light. The rate of energy loss matches Einstein's predictions perfectly. If gravity could be shielded or modified by intervening matter, we would see deviations when these systems pass behind other stars or through regions of interstellar gas and dust. We don't. Gravity passes through everything in the universe as if it weren't there. The LIGO and Virgo gravitational wave detectors have given us an entirely new way to study gravity. These instruments can detect ripples in spacetime caused by colliding black holes billions of light years away. The waves pass through Earth itself, through thousands of miles of rock and metal, without any attenuation except for the normal weakening with distance. When a gravitational wave passes through you, and they do, regularly, though far too weak to feel, it stretches and squeezes space itself, and there's nothing you can do to shield yourself from it. No Faraday cage for gravitational waves, no material that can block the stretching and squeezing of space itself. These experiments, carried out over centuries by thousands of dedicated scientists, all point to the same conclusion. Electric fields can be shielded because electric charge comes in 2 varieties that can cancel each other out, while gravitational fields cannot be shielded because mass comes in only 1 variety that always adds up. This isn't just an empirical observation, but a deep consequence of the mathematical structure of these forces, encoded in the different forms that Gauss's law takes for electricity and gravity. The mathematical beauty of Gauss's law deserves a moment of quiet appreciation. It tells us that fields and their sources are intimately connected, that you can't have one without the other. Electric field lines must begin on positive charges and end on negative charges. They can't just appear or disappear in empty space. Gravitational field lines must all point toward masses. They can't point away, can't form closed loops, can't do anything except flow inward toward their sources. These simple rules, expressed mathematically in Gauss's law, determine the entire structure of electromagnetic and gravitational fields throughout the universe. And here's something profound to contemplate. These laws appear to be exactly true everywhere in the universe. The light from distant galaxies billions of light years away shows the same electromagnetic behavior we see in our laboratories. The orbits of planets around other stars follow the same gravitational rules as the orbits in our solar system. The fundamental difference between shieldable electric fields and unshieldable gravitational fields appears to be a universal truth, not just a local peculiarity of our corner of the cosmos. As you lie there, perhaps feeling a bit sleepy now, surrounded by the quiet hum of electronic devices and held gently by Earth's gravity, you're experiencing both of these forces simultaneously. The electromagnetic fields from your devices are being shaped and channeled by conductors, blocked by shields, controlled and directed by human design. But the gravitational field passes through all of our technology as if it weren't there, connecting you directly to the Earth below, to the moon above, to the sun and planets and stars, with no intermediary, no filter, no possibility of disconnection. There's something both humbling and wonderful about this. We've learned to master electromagnetic fields, to bend them to our will, to use them to carry information and energy wherever we want. But gravity remains beyond our control, a constant reminder that we're part of something larger, something we can understand but not command. We can describe gravity with exquisite mathematical precision. We can predict its effects to extraordinary accuracy, but we cannot shield ourselves from it, cannot turn it off, cannot escape its patient, persistent pull. As we continue our gentle exploration tonight, I want to invite you to consider what it truly means to live in a universe where gravity cannot be shielded, where this one force reaches through everything, connecting all matter in an unbreakable web of mutual attraction. This isn't just a quirk of physics or an interesting scientific fact. It shapes everything about our existence, from the way we build our cities to the way we dream about the future, from the structure of our bodies to the rhythm of our days and nights. Think about the world we've built, the civilization that surrounds you right now. Almost everything in our modern world depends on our ability to control electromagnetic fields. The device you're listening to me on right now is a marvel of electromagnetic engineering, channeling electrons through carefully designed pathways, using magnetic fields to store information, converting electrical signals into sound waves that reach your ears. The walls around you probably contain miles of copper wire, each one a pathway for electromagnetic energy, each one surrounded by insulation that keeps the fields contained, directed, under control. When you fly in an airplane, the metal fuselage acts as a Faraday cage, protecting you and the sensitive electronics on board from lightning strikes and electromagnetic interference. A bolt of lightning can strike a plane, and it happens more often than you might think, about once per year for each commercial aircraft. But the electrical current flows around the metal shell and exits without harming anyone inside. The passengers might see a bright flash, might hear a loud bang, but they're safe inside their electromagnetic shield, protected by the same principle Faraday discovered in his metal room nearly 2 centuries ago. Our hospitals use electromagnetic shielding in profound ways. MRI machines, those remarkable devices that can peer inside your body without cutting you open, create magnetic fields tens of thousands of times stronger than Earth's. These fields are so strong they could pull iron objects across a room with lethal force. But step outside the MRI room, separated by walls lined with metal shielding, and you can't even tell the machine is on. The magnetic field that's strong enough to align the hydrogen atoms in your body to create detailed images of your internal organs is completely contained by electromagnetic shielding. But now imagine if we could shield gravity the same way. Imagine if we could build walls that gravity couldn't penetrate, create spaces where objects could float weightlessly, design buildings that didn't need to support their own weight. Our entire world would be transformed beyond recognition. Architecture would be limited only by imagination, not by the structural strength needed to resist gravity's pull. We could have buildings that float in the air, bridges made of gossamer thin materials, cities that drift through the sky like clouds. Transportation would be revolutionized. Instead of needing powerful rockets to reach orbit, we could simply turn off gravity and float up. Instead of cars that must push against friction and air resistance, we could have vehicles that glide effortlessly through 3-dimensional space. The energy requirements of our civilization would plummet. So much of what we do, so much of the energy we consume, is simply fighting against gravity, lifting things up, holding them in place, preventing them from falling down. But we don't live in that universe. We live in a universe where gravity is always there, always pulling, never resting, never shielded. And this constant, unshieldable presence of gravity has shaped not just our technology, but our very bodies, our evolution, our sense of what's normal and natural. Every bone in your body has evolved to resist gravity's pull. Your spine is a remarkable engineering structure, a flexible column that can support your weight while allowing you to bend and twist. Your heart has evolved to be strong enough to pump blood up to your brain against gravity's downward pull. Even your inner ear contains tiny organs specifically designed to detect gravity's direction, to tell you which way is up. Astronauts who spend months in the microgravity of the International Space Station experience profound changes to their bodies. Without gravity's constant pull, their bones begin to weaken, losing calcium at an alarming rate. Their muscles atrophy despite hours of exercise each day. Their cardiovascular systems adapt to not having to pump against gravity, making their hearts less efficient. When they return to Earth, they often can't stand up without help, can't walk without assistance, need weeks or months to readjust to the gravity they were born in but temporarily escaped. This tells us something profound. We are gravitational beings. Gravity isn't just something that affects us, it's something that has shaped us, molded us, made us what we are. Every cell in your body has evolved in a one-gravity environment. The way your blood vessels branch, the way your organs are arranged, the density of your bones, the strength of your muscles, all of these are precisely tuned to Earth's gravitational field. We are, in a very real sense, gravity-adapted creatures, as much a product of Earth's gravitational pull as we are of its atmosphere or its water. But let's think deeper about what Einstein revealed about gravity, because it adds another layer to why gravitational shielding is impossible. In Newton's picture, gravity was a force that reached across space to pull objects together. If it were just a force like electromagnetism, then maybe somehow we could find a way to block it. But Einstein showed us that gravity isn't really a force at all. It's the curvature of spacetime itself. Mass and energy bend the fabric of space and time, and objects moving through this curved spacetime follow the straightest possible paths, which we perceive as gravitational attraction. Imagine spacetime as a stretched rubber sheet. The classic analogy you've probably heard before. Place a bowling ball on this sheet and it creates a depression, a curvature in the surface. Now roll a marble near the bowling ball. The marble curves toward the bowling ball, not because of some invisible string pulling it, but because the surface itself is curved. The marble is actually following the straightest possible path on this curved surface, what mathematicians call a geodesic. Now here's the key insight. How do you shield yourself from the shape of space? How do you block geometry itself? It would be like trying to create a flat region on that curved rubber sheet without removing the bowling ball. The curvature is the very structure of the space you're moving through. You can't shield yourself from it any more than a two-dimensional being living on the surface of a sphere could shield itself from the sphere's curvature. The curvature isn't something passing through space that could be blocked. It is space. This geometric nature of gravity has profound implications for our earlier question about shielding. With electromagnetic fields, we're dealing with something that propagates through space, something that can be intercepted and cancelled. But with gravity, we're dealing with the shape of space itself. Every mass in the universe contributes to this shape, creating a complex landscape of curves and valleys that we navigate through our lives. The Earth creates a deep valley in space-time that we sit in, rolling around the sides but unable to climb out without tremendous energy. And here's where it gets even more interesting. Because gravity is the curvature of space-time, and because mass energy is what causes this curvature, and because of Einstein's famous equation E=mc2, even electromagnetic fields themselves gravitate. Light, which has no mass but does have energy, follows curved paths through gravitational fields. This has been observed countless times: starlight bending around the sun during eclipses, light from distant galaxies being lensed by massive galaxy clusters, even GPS satellites having to account for the way Earth's gravity affects the flow of time. This means that even if we could somehow create a region with no matter, a perfect vacuum, gravity would still exist there if there were electromagnetic fields present. The energy in those fields would curve space-time, creating gravitational effects. You can't escape gravity by removing all matter because energy itself gravitates. And since you can't have a region of space with absolutely no energy, quantum mechanics forbids it, demanding that even empty space seethes with virtual particles and zero-point energy. You can never have a region completely free of gravitational fields. Let me share with you a thought experiment that illustrates just how fundamentally different gravity is from electromagnetic forces. Imagine you're in a windowless room, and you want to determine whether you're sitting still on Earth's surface or accelerating through space at 1g. With electromagnetic fields, this would be easy. You could detect Earth's magnetic field, pick up radio waves from human transmitters, measure cosmic radiation patterns. All of these would tell you whether you're on Earth or in deep space. But with gravity alone, it's impossible to tell. This is Einstein's equivalence principle, one of the foundational insights of general relativity. Being at rest in a gravitational field is indistinguishable from accelerating in the absence of gravity. If you're in a closed box sitting on Earth, feeling your normal weight, there's no gravitational experiment you can do to distinguish this from being in a box accelerating upward at 9.8 meters per second squared in deep space. Gravity and acceleration are equivalent, two sides of the same coin. This equivalence principle is why astronauts feel weightless in orbit. They're not beyond Earth's gravity. At the altitude of the ISS, gravity is still about 90% as strong as on the surface. But they're in free fall, and when you're falling freely, you don't feel gravity. You and everything around you are falling together, following the same curved path through space-time, so there's no relative force between you and your surroundings. It's the closest thing we have to gravitational shielding, not blocking gravity, but moving with it so completely that it seems to disappear. But even this apparent escape from gravity is an illusion. The astronauts are still very much under gravity's influence, following an orbital path determined entirely by Earth's gravitational field. They've just found a way to fall that doesn't involve hitting the ground, falling around the Earth rather than into it. And maintaining this state requires precise velocities and altitudes. Too slow and you fall back to Earth. Too fast and you escape into interplanetary space. There's no stable configuration where you can just hover, weightless, without actively maintaining your orbit. This brings us to a profound realization about our place in the universe. We are not separate from the gravitational field that surrounds us, we are part of it. Every atom in your body contributes to the overall gravitational field of the universe. You bend space-time, even if only by an infinitesimally small amount. The Earth pulls on you, but you pull back on the Earth with exactly the same force. Newton's third law, every action has an equal and opposite reaction, applies to gravity just as it does to other forces. When you jump, you push the Earth away from you. The Earth is so massive that its acceleration is imperceptible. If you have a mass of 70 kilograms and you jump upward at 3 meters per second, you push the Earth downward at about 4 meters per second. But it's real. You've actually moved the entire planet, even if only by an amount smaller than an atom. This is the beautiful democracy of gravity. Everything pulls on everything else. Every mass influences every other mass, creating a vast web of mutual attraction that holds the universe together. And this web cannot be broken. Unlike electromagnetic forces, where you can have isolated systems, shielded regions, places where fields don't penetrate, gravity connects everything to everything else with no possibility of disconnection. The most distant galaxy you can see through a telescope is pulling on you right now with a force that's almost impossibly weak, but absolutely real. And you're pulling back on it. These gravitational relationships stretch across billions of light years, connecting all matter in the observable universe in a vast network of mutual influence. This universal, unshieldable nature of gravity has philosophical implications that go beyond physics. It means that true isolation is impossible. No matter how far you travel, no matter how alone you might feel, you remain connected to everything else through gravity. You can block light, block radio waves, block particle radiation, but you cannot block the gravitational connection that ties you to every star, every planet, every mote of dust in the cosmos. In a very real physical sense, we're all in this together, bound by forces we cannot escape. Consider what this means for the future of humanity. As we dream of spreading out into space, of colonizing other planets, of perhaps one day reaching other stars, we must always reckon with gravity. We can't simply turn it off for convenient space travel. We can't create gravity-free factories where delicate processes could be performed without the complication of weight. We can't shield our spacecraft from the gravitational influence of massive objects. Every journey through space is a careful dance with gravity, using it when helpful, fighting against it when necessary, but never escaping it. Our space probes use gravity assists, swinging around planets to gain speed and change direction, turning gravity from an obstacle into a tool. Our satellites occupy Lagrange points, special locations where the gravitational forces of Earth and Sun or Earth and Moon balance in just the right way to create stable orbits. Our future space elevators, if we ever build them, will be massive structures held up not by their own strength but by the balance between gravity pulling them down and centrifugal force pulling them out. Everything we do in space is shaped by gravity's unshieldable presence. Yet there's something beautiful about this constraint, this universal force we cannot escape. It means that the universe has a kind of coherence, a unity that transcends the vast distances between objects. Gravity is the force that gathered the primordial gas after the Big Bang into the first stars, that sculpted galaxies from cosmic chaos, that brought together the dust and gas that became our solar system, our Earth, and eventually us. Without gravity's patient, persistent, unshieldable pull, the universe would be a cold, diffuse cloud of atoms drifting apart forever. Gravity is the cosmic sculptor, the force that brings order from chaos, structure from randomness. Now, as we reach the contemplative heart of our journey tonight, I want us to slow down even more, To circle back to our central question with the patience of planets orbiting a star, returning again and again to the same fundamental mystery, but each time from a slightly different vantage point, each time perhaps seeing something we missed before. Why can't you shield yourself from gravity, but you can from electric fields? We've explored the physics, we've examined the experiments, we've contemplated the implications, but now let's approach it with the slow, meditative rhythm of deep understanding, the kind that comes not from rushing toward an answer, but from dwelling peacefully with a question. Feel yourself there, right now, wherever you are, held by gravity's patient embrace. Every molecule in your body knows which way is down, every cell has organized itself in response to this constant pull that has been with you since before you were born, since that first moment when you were just a single cell, beginning to divide and grow in your mother's womb, already under gravity's influence, already shaped by its presence. This force that you cannot shield yourself from has been your constant companion, more faithful than any friend, more persistent than any thought, always there whether you notice it or not, whether you think about it or not, whether you want it or not. And around you, flowing through you, there are electromagnetic fields, flickering and changing, blocked by some materials, channeled by others, creating a complex invisible landscape of forces that our technology has learned to navigate and control. Your phone connects to distant towers through electromagnetic waves that buildings partially block, that metal structures reflect and absorb, that weather can affect and interference can disrupt. These fields are contingent, variable, shapeable, controllable in ways that gravity never is, never can be, never will be according to everything we understand about the universe. Let's revisit this difference once more, but slowly, gently, like watching the tide come in, each wave reaching a little further up the beach, each cycle revealing something that was always there but perhaps not fully appreciated. Electric charges come in two varieties, positive and negative, plus and minus, the fundamental duality that allows for cancellation, for neutrality, for the possibility of creating regions where electric fields vanish. It's like having both silence and sound, darkness and light, hot and cold, opposites that can balance each other, cancel each other, create through their interaction a middle ground where neither dominates. When free charges in a conductor rearrange themselves to cancel an external electric field, they're doing something almost magical. They're creating exactly the right pattern, exactly the right distribution, to produce a field that perfectly opposes the one trying to penetrate their domain. It happens automatically, without thought or planning, just the natural consequence of charges seeking equilibrium, finding the configuration where no charge feels a net force. It's like water finding its level, but in the realm of electric fields, creating pools of electromagnetic calm in a stormy sea of forces. But mass, as far as we know, as far as we've ever seen, as far as our theories predict, comes in only one variety. There's no negative mass to balance positive mass, no anti-gravity to oppose gravity, no possibility of cancellation through careful arrangement. Every bit of mass in the universe pulls in the same direction, inward, toward itself, creating convergent field lines that never diverge, never cancel, never create regions of gravitational neutrality. It's as if the universe has only valleys and no peaks, only attraction and no repulsion, only gathering and no scattering, at least when it comes to gravity. And here we come to something profound about the nature of shielding itself. To shield generally means to create a barrier, to interpose something between yourself and a force or influence. But true shielding, the kind that works for electromagnetic fields, isn't really about blocking in the conventional sense. It's about creating conditions where fields cancel, where opposite influences balance, where the mathematics of superposition allows for zero as a possible outcome. Without opposites, without the possibility of cancellation, shielding becomes impossible not just practically, but conceptually, mathematically, fundamentally. The equivalence principle that Einstein discovered adds another layer to this impossibility. Let me take you through this slowly, because it's one of the most beautiful insights in all of physics. Imagine you're in an elevator, and suddenly the cable breaks. As you fall, you become weightless. You float inside the elevator, and if you release an object, it floats beside you. For those moments of free fall, gravity seems to have vanished. But has it really? No. You're still very much under gravity's influence, still accelerating toward Earth at 9.8 meters per second squared. It's just that you and the elevator and everything in it are all falling together, all following the same curved path through space-time. This is the closest thing we have to escaping gravity, not shielding ourselves from it, but moving with it so completely that we no longer feel its effects. Astronauts in orbit are in continuous free fall, always falling toward Earth but moving sideways fast enough that they keep missing it, following a curved path that takes them around and around our planet. They feel weightless, not because they've escaped gravity, but because they've surrendered to it completely, allowing it to guide their motion without resistance. But notice what this means. The only way to not feel gravity is to give in to it entirely, to follow exactly the path it dictates, to move precisely as it commands. You can't shield yourself from gravity. You can only surrender to it so completely that you no longer notice its presence. It's like trying to escape a river not by building a dam, but by becoming one with the current, flowing wherever it takes you. And even then, you're not really free of the river, you're just moving with it rather than against it. There's something almost philosophical about this, something that speaks to larger truths about resistance and acceptance, about the difference between fighting against something and flowing with it. With electromagnetic fields, we can resist, we can shield, we can say no, not here, not in this space. But with gravity, our only option is acceptance, surrender, moving with rather than against. We can use energy to temporarily oppose gravity, jumping up, flying in planes, launching rockets, but we can't create a space where gravity simply doesn't exist. Let me return once more to Gauss's law, this beautiful mathematical principle that encodes the difference between electric and gravitational fields. Picture a soap bubble floating in the air, its surface shimmering with rainbow colours. Now, imagine that this bubble can somehow detect and count field lines passing through its surface. For electric fields, Gauss's law tells us that the net number of field lines passing outward through the bubble equals the net charge inside. If there's a positive charge inside, field lines flow outward. If there's a negative charge, field lines flow inward. If there are equal positive and negative charges, the field lines that start on the positive charge end on the negative charge, never leaving the bubble, creating zero net flux through the surface. But for gravity, Gauss's law takes a different form. The gravitational field lines passing through our imaginary bubble all point inward if there's mass inside, all contributing in the same direction, all adding up rather than cancelling. There's no arrangement of masses that can create zero net flux, no configuration that produces a gravitational dead zone, no possible distribution that results in gravitational neutrality. The mathematics is implacable, absolute, allowing no exceptions, no loopholes, no clever arrangements that might circumvent this fundamental truth. And yet, there's something beautiful about this absoluteness, this universality of gravity. It means that gravity is the most democratic force in the universe, treating all matter equally, playing no favourites, making no exceptions. A gold atom and an iron atom, a proton and a neutron, a piece of ordinary matter and a piece of exotic matter. They all gravitate in exactly the same way, all follow the same rules, all contribute to and respond to gravitational fields identically. This is the equivalence principle in its deepest form. Not just that gravitational and inertial mass are the same, but that gravity is truly universal, truly impartial, truly incapable of discrimination. Scientists have tested this equivalence to extraordinary precision, looking for any hint that different materials might respond differently to gravity, that certain atomic structures or quantum states might provide some immunity or resistance to gravitational fields. They've dropped different elements in vacuum chambers, watching for any difference in acceleration. They've compared the orbits of satellites made from different materials. They've studied binary pulsars where ultra-dense neutron stars orbit each other, looking for any violation of gravitational universality. Always, always, always the answer is the same. Gravity treats everything identically, pulls on everything equally, cannot be resisted or shielded by any choice of material or configuration. Even antimatter, that exotic opposite of ordinary matter, seems to fall down rather than up. Recent experiments at CERN have finally been able to create and trap anti-hydrogen atoms long enough to watch them fall, and preliminary results suggest they fall just like regular hydrogen. If this holds up, and most physicists expect it will, It means that even antimatter doesn't provide an escape from gravity, doesn't offer a way to create gravitational cancellation, doesn't give us the negative mass we would need for gravitational shielding. So we return, again and again, to this fundamental asymmetry in nature. Electromagnetic fields can be shielded because electric charge comes in opposites that can cancel. Gravitational fields cannot be shielded because mass comes in only one variety that always adds up. This isn't a limitation of our technology or a gap in our knowledge. It appears to be a fundamental feature of the universe, as basic as the fact that space has 3 dimensions or that time flows forward. But let's go deeper still, into the quantum realm, where the very nature of fields becomes strange and probabilistic. In quantum field theory, forces are carried by virtual particles, photons for electromagnetism, hypothetical gravitons for gravity. Virtual photons can be absorbed and emitted by charged particles. Their effects can be blocked by barriers that absorb or reflect them. But virtual gravitons, if they exist, would be emitted and absorbed by anything with energy, and everything has energy. Even empty space has zero-point energy. How do you shield yourself from particles that are emitted and absorbed by the very fabric of spacetime itself? This quantum perspective adds yet another layer to the impossibility of gravitational shielding. In the electromagnetic case, we can have regions with no charged particles, regions where virtual photons have nothing to interact with. But in the gravitational case, the virtual gravitons would interact with the energy of the electromagnetic field itself, with the mass energy of the shield we're trying to use, with the quantum fluctuations of empty space. There's no such thing as a gravitationally neutral region because there's no such thing as a region with absolutely no energy. As we circle around this question, approaching it from different angles, different perspectives, different levels of understanding, a pattern emerges. The impossibility of gravitational shielding isn't just one thing, it's many things, all pointing to the same conclusion. It's the single sign of mass versus the dual signs of charge. It's the geometric nature of gravity versus the force nature of electromagnetism. It's the universality of gravitational coupling versus the selectivity of electromagnetic coupling. It's the quantum mechanical inevitability of energy everywhere versus the possibility of charge-free regions. All of these different perspectives, different frameworks, different ways of understanding physics, they all converge on the same truth. You cannot shield gravity. And perhaps this is how deep truths about the universe reveal themselves, not through a single decisive experiment or a single brilliant insight, but through a convergence of evidence from many directions, a consistency across different frameworks, a harmony between different ways of understanding. The impossibility of gravitational shielding is written into the universe at every level, from the cosmic to the quantum, from the mathematical to the experimental, from the theoretical to the practical. As you lie there, feeling the gentle, constant pull of gravity, you're experiencing one of the universe's most fundamental truths directly, physically, undeniably. You cannot shield yourself from this force, cannot hide from it, cannot escape it. But perhaps that's not a limitation. Perhaps it's a connection, a reminder that you're part of something vast and unified, something that includes every star you see and countless ones you don't, every planet, every moon, every drifting grain of cosmic dust. Gravity is the thread that weaves the universe together, and you cannot cut yourself free from this thread, because you are not separate from the tapestry. You are part of it, woven into it, held by it, and holding it in return. This is where our contemplation has brought us, not to a solution that lets us escape gravity, but to an understanding of why we cannot and perhaps should not want to. Gravity's unshieldable nature is not a bug, but a feature, not a limitation, but a connection, not a chain, but the embrace that holds the universe together and holds us within it, part of the grand gravitational dance that has been going on since the first moments after the Big Bang, and will continue until the universe's final chapter, whatever that may be. In the quiet spaces between certainty and speculation, between what we know and what we wonder about, there exists a realm of gentle possibilities, of experiments that push against the boundaries of our understanding, of theories that whisper about realities we haven't yet discovered. Tonight, as we continue our exploration of why gravity cannot be shielded while electric fields can, I want to take you into this liminal space, this borderland where science meets imagination, where rigorous measurement meets creative speculation, where the known edges softly into the unknown. Let me tell you about the observatories that listen to the universe in ways our ancestors could never have imagined. Deep underground in Louisiana and Washington State, in Italy and Japan, instruments of almost impossible sensitivity wait in the darkness for the faintest whispers of gravitational waves, ripples in space-time itself that travel across the cosmos at the speed of light. These detectors, LIGO and Virgo and Cagra, are so sensitive they can measure distances that change by less than 1,000th of the width of a proton, detecting the stretching and squeezing of space itself as gravitational waves pass through Earth. When two black holes spiral into each other 1 billion light-years away, when neutron stars collide in cosmic violence that forges heavy elements like gold and platinum, these events send out gravitational waves that eventually reach Earth, passing through our planet, through the detectors, through you and me, stretching and squeezing space itself by an amount so small it seems impossible to measure. And yet we do measure it, confirming Einstein's predictions from a century ago, showing us that gravity propagates as waves through the fabric of space-time itself. What's remarkable about these gravitational waves, what speaks directly to our question tonight, is that nothing can shield them. They pass through Earth itself as if it weren't there, through thousands of miles of rock and metal and molten iron without any attenuation except the normal weakening with distance. When a gravitational wave passes through you, and they do, these cosmic ripples washing over Earth regularly, there's nothing you can do to block them, no material you can hide behind, no Faraday cage equivalent that could protect you from the stretching and squeezing of space itself. This is profoundly different from electromagnetic waves. Radio waves can be blocked by metal, absorbed by water, scattered by the atmosphere. Light can be stopped by opaque materials, reflected by mirrors, refracted by lenses. Even gamma rays, the most penetrating form of electromagnetic radiation, can be shielded with enough lead or concrete. But gravitational waves pass through everything, carrying information about cosmic catastrophes directly to our detectors, without any possibility of interference or shielding. The implications of this are staggering. It means we can see the universe in a fundamentally new way, peering through dust clouds and stellar atmospheres that would block electromagnetic radiation, detecting events that happened inside dense stellar cores where light could never escape. It's like suddenly being able to hear after a lifetime of deafness, discovering that the universe is full of gravitational songs we never knew existed. And none of these songs can be muted, none of these waves can be blocked, because they're not really waves in space, but waves of space itself. But let's explore some of the more speculative ideas that scientists have considered, the gentle possibilities that remain open even if unlikely. Throughout history, there have been claims of anti-gravity effects, of materials or configurations that might shield or modify gravitational fields. Most of these have turned out to be experimental errors or misunderstandings, but the search continues because the implications would be so profound if even a tiny effect were found. In the 1990s, a Russian researcher named Eugene Podkletnov claimed to have observed a gravitational shielding effect above a spinning superconductor. He reported that objects placed above his device seemed to lose a small fraction of their weight, as if the superconductor were partially blocking Earth's gravitational field. The scientific community was skeptical but intrigued. NASA even funded research to try to replicate the effect. Teams around the world built similar devices, carefully measuring any changes in gravitational force. The result? No reproducible effect. Whatever Podkletnov thought he saw, it wasn't gravitational shielding. But the search hasn't stopped. Scientists continue to explore whether exotic states of matter might interact with gravity in unexpected ways. Superconductors, with their ability to expel magnetic fields completely, seemed like promising candidates. Perhaps, some theorized, there might be a gravitational equivalent to the Meissner effect, where gravitational fields would be expelled from certain materials under certain conditions. Careful experiments have found no such effect, but the possibility remains a subject of theoretical investigation. There's also the mysterious dark energy that appears to be causing the universe's expansion to accelerate. This energy seems to have a kind of anti-gravitational effect, pushing space apart rather than pulling it together. Could we somehow harness dark energy to create regions of gravitational repulsion? Could we use it to shield ourselves from gravity? The honest answer is we don't know. We don't even know what dark energy is, let alone how to manipulate it. It remains one of the deepest mysteries in physics, a gentle reminder that our understanding of gravity itself may be incomplete. Some theorists have explored whether extra dimensions, if they exist, might provide a backdoor to gravitational shielding. In theories with large extra dimensions, gravity might be able to spread into these dimensions, while other forces remain confined to our familiar three-dimensional space. Could we somehow use these extra dimensions to redirect gravitational fields to create shadows or shields? It's a beautiful idea, but one that remains purely theoretical. We have no evidence that large extra dimensions exist, and even if they do, we have no idea how to access or manipulate them. Quantum mechanics adds its own layer of mystery to gravity. While we have successful quantum theories of the electromagnetic, weak and strong forces, gravity stubbornly resists quantization. We don't have a complete quantum theory of gravity, which means we don't fully understand how gravity behaves at the smallest scales, in the realm of atoms and subatomic particles. Could quantum gravitational effects provide some way to shield or modify gravitational fields? Perhaps, but we're so far from understanding quantum gravity that we can barely formulate the question properly, let alone answer it. There's something called the Casimir effect that demonstrates how quantum fluctuations can create measurable forces. Between two closely spaced metal plates, certain wavelengths of quantum fluctuations are excluded, creating a pressure difference that pushes the plates together. Some researchers have wondered whether a similar effect might exist for gravitational fluctuations, whether we might be able to create regions where gravitational effects are modified by quantum phenomena. So far, no such effect has been observed, but the intersection of quantum mechanics and gravity remains largely unexplored territory. Let me share with you one of the most precise experiments ever conducted in the search for gravitational anomalies. At the University of Washington, researchers built what they call the Wirtwash experiment, a modern version of the classical Wirtwas experiment that tests whether different materials fall at the same rate in a gravitational field. Their apparatus can detect differences in acceleration as small as 1 part in a quadrillion. They've tested everything from ordinary metals to exotic materials, from different isotopes to complex molecular structures. Always, the result is the same. Everything falls at exactly the same rate. Gravity treats all matter identically. There's no material that provides any special immunity or resistance to gravitational fields. Even more exotic possibilities have been considered. What about negative mass, not antimatter, which has positive mass as far as we can tell, but truly negative mass that would gravitationally repel rather than attract? Such material would have bizarre properties. Push it, and it would accelerate toward you rather than away. Pair it with positive mass, and both would accelerate together in the same direction forever, violating conservation of momentum as we understand it. Most physicists believe negative mass is impossible, that it would lead to logical paradoxes and violations of fundamental principles. But until we have a complete theory of quantum gravity, we can't absolutely rule it out. There's also the question of whether information itself might gravitate differently than matter and energy. Information has entropy. Entropy is related to energy through thermodynamics, and energy gravitates according to Einstein's equations. But could there be subtle effects, quantum informational aspects of gravity that we haven't yet discovered? Could the way information is encoded or processed affect gravitational fields in ways our current theories don't predict? These are questions at the very edge of theoretical physics, where speculation blends with rigorous mathematics in ways that might seem like science fiction, but could hold seeds of future discoveries. Some researchers have explored whether rotating masses might produce gravitational effects analogous to magnetism. Just as moving electric charges create magnetic fields, rotating masses create what's called gravitomagnetism, or frame dragging, a tiny effect where the rotation of a massive object like Earth slightly drags spacetime around with it. This effect has been measured by satellites and matches Einstein's predictions perfectly. But could there be ways to enhance or manipulate these gravitomagnetic effects to create some form of gravitational shielding? So far, the answer appears to be no, but the mathematics of rotating spacetimes is complex enough that surprises might still be possible. The recent discovery of gravitational waves has opened up entirely new ways to study gravity. As our detectors become more sensitive, we're able to observe smaller and smaller effects, testing general relativity in regimes where it's never been tested before. So far, every observation matches Einstein's predictions with extraordinary precision. The waves propagate at exactly the speed of light, they carry energy and angular momentum as predicted, they interact with matter in exactly the way the equations say they should. There's no hint of any deviation that might suggest ways to shield or modify gravitational effects. But perhaps the most profound evidence for the unshieldable nature of gravity comes from cosmology, from our observations of the universe on the larger scales. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, we see tiny fluctuations that were caused by gravitational effects in the early universe. These patterns tell us that gravity has worked the same way for 13.8 billion years, that its properties haven't changed, that there's no evidence of any cosmic regions where gravity behaves differently or can be shielded. Galaxy clusters, those enormous congregations of thousands of galaxies bound together by gravity, show us gravity working on scales of millions of light years. The way galaxies orbit within clusters, the way clusters themselves move and merge, the way light from distant galaxies is bent by the gravitational fields of intervening clusters. All of this matches our understanding of gravity as an unshieldable, universal force that affects everything equally. If there were ways to shield gravity, if certain materials or configurations could block gravitational fields, we would see evidence of it in these cosmic structures. We don't. Even the search for dark matter, that mysterious substance that seems to make up most of the matter in the universe, tells us about gravity's unshieldable nature. Dark matter interacts gravitationally but not electromagnetically. We can see its gravitational effects on galaxies and clusters, but it doesn't emit or absorb light. If gravitational shielding were possible, dark matter would presumably use it to create structures invisible to gravitational detection, as well as electromagnetic. But we see dark matter's gravitational influence everywhere we look, suggesting that even this exotic form of matter cannot shield itself from gravity. The search for gravitational shielding has also led to better understanding of what we can do with gravity. We can't shield it, but we can use it in remarkable ways. Gravitational lensing allows us to use galaxy clusters as natural telescopes, magnifying distant galaxies that would otherwise be too faint to see. Gravitational time dilation, the slowing of time in strong gravitational fields, must be accounted for in GPS satellites to maintain accurate positioning. Gravitational assists allow our spacecraft to gain speed and change direction by swinging around planets, turning gravity from an obstacle into a tool. And in the realm of theoretical physics, the impossibility of gravitational shielding has led to deep insights about the nature of space and time. The fact that gravity is universal, that it affects everything equally, that it cannot be shielded or blocked. These aren't just empirical observations, but fundamental features that any theory of quantum gravity must explain. They're constraints that guide theorists toward the correct description of how gravity works at the deepest level. As we contemplate these possibilities and impossibilities, these experiments and observations, these theories and speculations, a picture emerges of gravity as something fundamentally different from the other forces of nature. Not just in its weakness. Gravity is by far the weakest force, weaker than electromagnetism by a factor of about 1036, but in its universality, its unshieldability, its geometric nature. Gravity isn't just another force, it's the curvature of the stage on which all other forces play out. Perhaps one day we'll discover something that changes our understanding, some exotic phenomenon or clever configuration that allows for gravitational shielding. Science is full of surprises, full of moments when what seemed impossible becomes possible, when what appeared to be fundamental, limits turn out to be only temporary barriers. But for now, all evidence points to the same conclusion. Gravity cannot be shielded, cannot be blocked, cannot be escaped. It is the universal force that binds the cosmos together, and we are all, always, inevitably part of its embrace. Here you are, a collection of atoms arranged in a pattern complex enough to contemplate its own existence, lying in the darkness perhaps, or maybe the soft light of evening is filtering through your window, and you're thinking about forces you cannot see, fields you cannot touch, the invisible architecture that shapes every moment of your existence. There's something profound about being a conscious being in a universe of forces and fields, something that deserves our quiet contemplation as we near the end of our journey tonight. You are, in this very moment, a gravitational being having a gravitational experience. Every cell in your body has evolved under the constant pull of Earth's gravity. every organ arranged to function in this one gravity environment we call home. Your heart, that remarkable pump, has developed exactly the right strength to push blood up to your brain against gravity's downward pull, maintaining the pressure needed to keep you conscious and aware. Too weak, and you'd faint every time you stood up. Too strong, and the pressure would damage delicate vessels when you lie down. Evolution has tuned your cardiovascular system to Earth's gravitational field with exquisite precision. Your bones, those living structures that hold you upright, are constantly remodeling themselves in response to gravitational stress. The cells that build bone, osteoblasts, and the cells that break it down, osteoclasts, maintain a delicate balance, adding material where gravity's stress is greatest, removing it where it's not needed. This is why astronauts lose bone density in space. Without gravity's constant loading, their bodies literally forget how to maintain proper bone structure. We are sculptured by gravity, shaped by it at the cellular level, our very architecture a response to its unceasing pull. But we're not just physical beings shaped by gravity, we're conscious entities capable of understanding it, describing it with mathematics, measuring it with incredible precision. Think about what this means. The same gravity that shapes your bones and blood vessels has also shaped your brain. That 3-pound universe of neurons that somehow gives rise to consciousness, to the ability to wonder about gravity itself. You are gravity contemplating gravity, mass thinking about mass, the universe developing the capacity to understand itself. There's a beautiful recursion here, a kind of cosmic self-reference. Your brain, made of atoms forged in the hearts of dying stars and gathered together by gravity, has developed the ability to understand the very force that assembled it. When you think about gravitational fields, when you imagine field lines converging on masses, when you contemplate why gravity can't be shielded, you're using a gravitationally assembled structure to understand gravitational assembly. It's like a wave contemplating the ocean, a whirlpool understanding fluid dynamics. And consider the words we use to describe our emotional states, how deeply gravity has influenced even our language and metaphors. We feel heavy with sadness, light with joy. We talk about grave situations, weighty matters, falling in love. Depression is often described as feeling like increased gravity, everything requiring more effort, harder to move, harder to rise. Happiness is described as floating, as lightness, as defying gravity. Our emotional vocabulary is suffused with gravitational metaphors, as if our psyches themselves are shaped by our constant negotiation with this force. When you're tired, you feel gravity more acutely. Your limbs feel heavier, your eyelids harder to keep open, your whole body wanting to surrender to gravity's patient pull. Sleep itself is a kind of gravitational surrender, a daily acceptance of our need to lie down, to stop fighting against gravity for a while, and let our bodies rest horizontally, our hearts no longer working against that vertical gradient, our muscles relaxing from their constant anti-gravity work. We spend a third of our lives in this horizontal position, giving in to gravity completely, letting it hold us while we dream. And what about those dreams? Even in our sleeping minds, gravity often maintains its rules. Most people report that in their dreams, gravity usually works normally. Objects fall down, they walk on the ground, water flows downhill. But sometimes, gloriously, we dream of flying, of floating, of escaping gravity's bonds. These flying dreams are often described as the most euphoric, the most liberating, as if some deep part of us yearns to be free from this constant force. Yet even these dreams of gravitational freedom are defined by gravity. They're meaningful precisely because they represent an escape from something we can never actually escape while awake. Our technologies, too, are profoundly shaped by our inability to shield gravity. Every building is a negotiation with gravity, every bridge a careful balance of forces designed to channel gravity's pull safely to the ground. We build with compression and tension, with arches and cables, with materials whose primary job is to resist gravity's patient efforts to pull everything down. If we could shield gravity, architecture would be limited only by imagination. Buildings could float, bridges could be made of gossamer, we could have cities in the clouds. But we can't, so we build with steel and concrete, with foundations that go deep into the earth, with massive structures whose strength is dedicated almost entirely to resisting gravitational collapse. Think about how different our world is when it comes to electromagnetic shielding versus our inability to shield gravity. You can turn off your Wi-Fi router and create an electromagnetic quiet zone in your home. You can put your phone in airplane mode and disconnect from the electromagnetic chatter of civilization. You can wrap sensitive electronics in metal shielding to protect them from interference. But you cannot turn off gravity, cannot create a gravitational quiet zone, cannot take a break from its constant presence. It's always there, always pulling, always demanding that we account for it in everything we do. This has profound implications for how we relate to the universe. With electromagnetic fields, we can choose our level of engagement. We can shield ourselves, isolate ourselves, create private electromagnetic spaces where outside influences don't penetrate. But with gravity, we're always connected, always participating in the gravitational network of the universe. Every mass pulls on every other mass, no exceptions, no opt-outs, no privacy settings. We are gravitationally naked to the universe, unable to hide our mass, unable to prevent it from influencing and being influenced by everything else. There's something both vulnerable and beautiful about this forced participation. You cannot gravitationally ghost the universe. You cannot put up gravitational walls. You cannot refuse to play the gravitational game. Simply by existing, by having mass, you're part of the cosmic gravitational community. The farthest galaxy pulls on you, and you pull back. The loneliest asteroid in the emptiest region of space still feels your gravitational influence, however faint. You are, whether you like it or not, in relationship with everything. And what does it mean that our minds, these remarkable patterns of electrical and chemical activity, can understand something as abstract as field lines and Gauss's law? The neurons in your brain communicate through electromagnetic effects, ions flowing through channels, creating electrical potentials, generating tiny magnetic fields. Your thoughts are, in a very real sense, electromagnetic phenomena, and these electromagnetic patterns have developed the ability to understand both electromagnetic and gravitational fields, to see the deep difference between them, to comprehend why one can be shielded and the other cannot. When you learn physics, when you understand why gravity can't be shielded, you're doing something extraordinary. You're using a brain shaped by gravity and operating through electromagnetism to understand both forces at an abstract mathematical level. You're transcending your immediate sensory experience to grasp universal principles that apply everywhere in the cosmos. A being that evolved to find food and avoid predators on the African savanna has developed the capacity to understand the gravitational waves from colliding black holes billions of light years away. If that's not a kind of miracle, I don't know what is. Consider how we measure time itself, how gravity affects our most basic coordinate for organizing, experience. Einstein showed us that time runs slower in stronger gravitational fields, that clocks at sea level run slower than clocks on mountaintops, that GPS satellites have to account for gravitational time dilation to maintain accuracy. Your head, being slightly farther from Earth's center than your feet, ages slightly faster, by about 90 nanoseconds per year if you're lying down, a bit more if you're standing up. You are a temporal gradient, aging at different rates at different heights, though the effect is far too small to notice. This gravitational influence on time means that gravity shapes not just space, but history itself. The universe's story, from the Big Bang to now, has been paced by gravity. The rate at which stars form and die, the speed at which galaxies evolve, the tempo of cosmic evolution itself, all of these are governed by gravity's patient orchestration. And because gravity can't be shielded, this cosmic tempo penetrates everywhere, setting the rhythm for every process in the universe, from the fusion in stellar cores to the biochemistry in your cells. We live in an electromagnetic civilization built on a gravitational foundation. Our cities glow with electromagnetic radiation, lights, radio waves, Wi-Fi signals, cellular transmissions. We've learned to shape and control these electromagnetic fields with extraordinary precision, creating the complex electromagnetic ecosystem that modern life depends on. But underneath it all, holding it all down, keeping it all grounded, is gravity, unshielded, unblocked, unchangeable. Every electromagnetic device must also be a gravitational device, built strong enough to support its own weight, designed to function in Earth's gravitational field. And here's something to contemplate. We understand electromagnetism well enough to manipulate it at will, to create technologies that would seem like magic to our ancestors. But our understanding of gravity, despite Einstein's beautiful general relativity, remains incomplete. We don't know how to quantize it, don't understand how it behaves at the smallest scales, don't know how to reconcile it with quantum mechanics. The force we can't shield is also the force we don't fully understand. There's a deep mystery here, a puzzle that the greatest minds in physics are still working to solve. What would it mean for humanity if we could shield gravity? It would be the most transformative discovery in history, more revolutionary than fire, than electricity, than nuclear power. Space travel would become trivial. We could build cities that float in the air, vehicles that never touch the ground, manufacturing facilities where delicate processes happen in perfect weightlessness. The energy requirements of civilization would plummet, but perhaps more profoundly, it would change our relationship with the universe. We would no longer be mandatory participants in the cosmic gravitational network. We could choose when to engage and when to withdraw, when to feel weight and when to float free, but we can't. And perhaps there's wisdom in this limitation. Gravity's unshieldable nature keeps us grounded, literally and figuratively. It ensures that we remain connected to Earth, to each other, to the cosmos. It prevents us from floating away into isolation, from severing our connections with the physical world. It makes us participants rather than observers, actors rather than audience members in the cosmic drama. As you lie there, feeling gravity's familiar pull, you might notice how your breathing works with and against gravity. When you inhale, your diaphragm contracts downward, working with gravity. When you exhale lying on your back, gravity helps push the air out. But when you're standing, breathing requires more work against gravity to expand your chest upward. Even this most basic life function, this constant rhythm of breath, is shaped by our gravitational environment. Astronauts report that breathing feels different in space, that without gravity's familiar resistance, the simple act of respiration becomes strange, foreign, requiring conscious adjustment. Our sense of balance, too, is fundamentally gravitational. The vestibular system in your inner ear contains tiny crystals called otoliths that shift in response to gravity and acceleration, telling your brain which way is up. This system evolved specifically to detect gravity's direction, to help us maintain our orientation in a gravitational field. When this system is disrupted, by illness, by unusual accelerations, by the absence of gravity in space, we experience vertigo, nausea, profound disorientation. We are so fundamentally gravitational beings that removing gravity makes us literally sick until we adapt. Think about water, how it behaves in gravity versus without it. Here on Earth, water flows downhill, forms droplets that fall, creates surfaces that are level. Pour water and it flows down, pools at the lowest point, finds its level through gravity's organizing influence. But in the microgravity of space, water behaves completely differently. It forms floating spheres, adheres to surfaces through surface tension, doesn't flow or pour in any familiar way. Astronauts can't take showers. They have to use wet wipes. They can't pour a cup of coffee. They have to sip from pouches. Gravity organizes fluids in ways we take for granted until they're gone. Even eating is gravitational. Swallowing relies partly on gravity to help move food down your esophagus to your stomach. In space, astronauts can still swallow. The muscles of the esophagus can push food along without gravity's help, but it feels different, requires more conscious effort. Our entire digestive system evolved in a gravitational environment where up and down have meaning, where things naturally flow downward, where gas rises and liquids sink. The simple act of digestion becomes complicated when gravity is removed. Now, as we move into the deeper, quieter hours of our contemplation, let the rhythm of our exploration slow even further, like a river approaching the sea, spreading out, becoming calmer, more reflective. We've travelled far tonight, from the electric fields you can shield with simple aluminum foil to the gravitational waves that pass through entire planets unchanged, from the mathematics of Gauss's law to the philosophy of forced universal connection. Let's allow all of these ideas to settle gently, like sediment in still water, forming layers of understanding that don't require sharp focus or intense concentration, just a soft awareness, a peaceful recognition of the patterns we've discovered. You're still feeling it right now, That patient pull that never stops, never varies, never gives you a moment's break from its presence. Gravity. Always there, always pulling. While electric fields flicker and change around you, your phone receiving signals, then going quiet, Wi-Fi routers cycling on and off, the electromagnetic landscape constantly shifting like weather, gravity remains constant, unchanging, as reliable as anything in the universe can be. The Earth pulls on you with the same force now as it did an hour ago, as it did yesterday, as it did when you were born. This constancy, this absolute reliability, it's both comforting and inescapable. We've seen how electric charge comes in positive and negative, plus and minus opposites that can cancel, creating the possibility of neutral regions, quiet zones, shielded spaces where electric fields cannot reach. Like noise-cancelling headphones that create silence through carefully crafted opposing sound waves, conductors can create electromagnetic silence through the automatic rearrangement of charges. It's elegant, this ability of nature to create cancellation, to allow for zeros, for nulls, for quiet spaces in the electromagnetic storm. But mass, as far as we know, as far as we've ever seen, as far as our theories predict, comes only in one variety. Positive mass, attractive mass, inward pulling mass. There's no negative mass to balance it, no anti-gravity to oppose it, no possibility of cancellation through careful arrangement. Every atom adds to the gravitational field, every molecule contributes its small pull, every speck of dust, every drop of water, every breath of air. They all pull inward, all attract, all contribute to the universal gravitational field that permeates space. Gauss's law, that beautiful mathematical principle we've returned to again and again, encodes this difference in its very structure. For electric fields, the flux through a surface depends on the net charge inside, positive minus negative, a sum that can be zero. For gravitational fields, the flux depends on the total mass inside, all positive, always adding, never cancelling. The mathematics doesn't allow for gravitational shielding because the sources don't allow for cancellation. It's not a limitation of our technology or a gap in our knowledge, it's built into the fundamental structure of the fields themselves, and beneath this mathematical truth lies an even deeper one. Einstein's recognition that gravity isn't really a force at all, but the curvature of space-time itself. Mass and energy bend the fabric of space and time, creating valleys and slopes that we perceive as gravitational attraction. How do you shield yourself from the shape of space? How do you block geometry itself? It would be like trying to create a flat spot on a curved surface without changing the surface itself, a logical impossibility, a contradiction in terms. The experiments we've discussed, from Cavendish's delicate torsion balance to the modern LIGO detectors that can measure distortions smaller than an atomic nucleus, all confirm this same truth. Gravity passes through everything. No material blocks it. No configuration shields it. No arrangement of matter creates gravitational shadows or quiet zones. The gravitational field penetrates all substances with perfect indifference, as if they weren't even there. Even our most exotic theories, our most creative speculations haven't found a way around this. Antimatter falls down, not up. Superconductors don't expel gravitational fields the way they expel magnetic ones. Dark energy, mysterious as it is, doesn't give us a way to shield gravity, only a way to accelerate the expansion of space itself. Extra dimensions, if they exist, don't provide an escape route from gravitational fields. Quantum mechanics, for all its strangeness, doesn't offer any loopholes that would allow gravitational shielding. We've explored how this unshieldable nature of gravity shapes our technology, our architecture, our very bodies. Every building must support its own weight. Every bridge must channel gravitational forces safely to the ground. Every rocket must have enough power to climb out of Earth's gravitational well. Our bones must be strong enough to support us. Our hearts must be powerful enough to pump blood upward against gravity. We are engineered by evolution and engineering to function in an unshieldable gravitational field, and we've contemplated what this means philosophically, emotionally, spiritually even. We cannot disconnect from the gravitational network of the universe. We cannot opt out of the cosmic gravitational community. We're always connected to everything else, always pulling and being pulled, always participating in the gravitational dance that holds galaxies together and keeps planets in their orbits. This forced participation, this inability to achieve gravitational privacy, makes us permanent citizens of the cosmos, forever linked to every other mass in the universe. The equivalence principle adds another layer to our understanding. Freefall is the only way to not feel gravity, and it's not really an escape but a complete surrender, following the curved paths through space-time that mass has created. Astronauts in orbit aren't beyond gravity. They're in continuous, free fall, and their weightlessness is the weightlessness of falling, not the weightlessness of escape. Even this apparent freedom from gravity is actually the deepest submission to it. As these ideas wash over you, as they settle into that quiet place where understanding lives not as sharp knowledge but as gentle awareness, you might notice that you don't need to grasp every detail, remember every equation, recall every experiment. The essential truth is simple enough to feel in your bones. Electric fields can be shielded because electric charges can cancel each other out, while gravitational fields cannot be shielded because mass only adds up, never cancels. This asymmetry is woven into the fabric of reality itself. Let your mind drift now through the implications of this truth, not forcing connections but allowing them to arise naturally, like bubbles rising through still water. If gravity could be shielded, the universe would be fundamentally different. Stars might not form, or they might form differently. Galaxies might not hold together. Planets might not orbit suns. The cosmic web of dark matter that provides the scaffolding for visible matter might not exist. Life itself, which depends on stable planetary orbits and reliable gravitational conditions, might never have arisen. Perhaps the impossibility of gravitational shielding is not a limitation but a necessity, not a restriction but a requirement for a universe capable of complexity, structure, and ultimately consciousness. Perhaps a universe where gravity could be shielded would be a universe where nothing interesting could happen, where matter couldn't congregate into stars and planets, where the delicate conditions necessary for life could never arise. The very fact that we're here to wonder about gravitational shielding might depend on its impossibility. There's a deep beauty in this thought, that the universe's apparent limitations might actually be the conditions necessary for our existence. The forces that we cannot escape might be the forces that make us possible. The connections we cannot sever might be the connections that allow us to exist in the first place. We are here because gravity cannot be shielded, not in spite of it. And as you lie there, feeling the constant pull that connects you to Earth, to the moon, to the sun, to every star you can see and countless ones you cannot, you might feel a sense of belonging that transcends the merely physical. You are not a separate entity that happens to be affected by gravity. You are a gravitational entity, a knot in the gravitational field, a place where the universe has gathered matter together tightly enough to think about itself. Your mass, small as it is on the cosmic scale, contributes to the overall gravitational field of the universe. You bend space-time, even if only by an infinitesimal amount. The gravitational waves from distant cosmic events pass through you, and you add your own tiny contribution to their propagation. You're not just subject to gravity. You're part of the gravitational structure of the universe, a participant in the cosmic gravitational symphony, even if your note is too quiet to hear above the cosmic chorus. This is what we've discovered tonight through our gentle exploration. Not just that gravity can't be shielded, but what this impossibility means for our understanding of the universe and our place in it. We've found that the difference between shieldable electric fields and unshieldable gravitational fields reflects a deep asymmetry in nature, one that shapes everything from subatomic particles to galaxy clusters, from the evolution of our bodies to the structure of our civilization. The mathematics tells us why. Gauss's law with its different forms for electricity and gravity, the bipolar nature of charge versus the monopolar nature of mass, the geometric interpretation of gravity as curved space-time rather than a force. The experiments confirm it, centuries of careful measurements finding no exception, no material that blocks gravity, no configuration that creates gravitational shadows. The implications surround us. In our buildings that must resist gravitational collapse, our bodies that evolved in constant gravity, our dreams of flight that represent escape from the inescapable. As the night deepens and your thoughts begin to soften towards sleep, let these ideas continue their gentle circulation, not as problems to be solved, but as truths to be appreciated. The universe has given us forces we can control, and forces we cannot, connections we can sever, and connections we cannot escape, fields we can shape, and fields that shape us whether we will it or not. In this interplay of control and submission, of agency and acceptance, we find our place in the cosmic order. The question we began with, why can't you shield yourself from gravity but you can from electric fields, has led us not to a simple answer, but to a deep appreciation of the universe's structure. We've found that this impossibility is not a bug but a feature, not a limitation but a foundation, not a restriction but a connection that binds the universe together and us within it. And now, as we approach the end of our journey together tonight, as the ideas we've explored begin to settle like dust in moonlight, let's return once more to where we began, to you lying there, feeling the gentle, insistent pull of gravity that has been your companion since before you were born and will continue until the universe itself grows cold and still. But now, perhaps, you feel it differently, understand it differently, appreciate it in a way you didn't before we began this quiet exploration together. You started this evening aware of gravity in the way we're all aware of it, as weight, as the force that keeps things down, as the reason we need stairs and elevators, the reason things fall when dropped. But now you know it as something more profound, as the curvature of space-time itself, as the one force that cannot be shielded, as the universal connector that links every mass to every other mass across the vast emptiness of space. You know it as the force that shaped your bones and blood vessels, that times your heartbeat and breathing, that gave the universe its structure and Earth its orbit. Around you right now, electromagnetic fields flicker and dance, carrying information through Wi-Fi and cellular signals, powering the devices of modern life, creating the complex electromagnetic ecosystem we've built our civilization upon. These fields can be blocked by walls, redirected by conductors, cancelled by careful arrangement of charges. You can create electromagnetic quiet zones, Faraday cages where these fields cannot penetrate, spaces of electromagnetic silence in the midst of the electromagnetic storm. This ability to shield, to control, to shape electromagnetic fields is what makes our technology possible. But the gravitational field that permeates your room, your body, your every atom, it cannot be blocked, cannot be redirected, cannot be cancelled. It passes through walls as if they weren't there, through the entire Earth without attenuation, through you right now with perfect indifference to your desires or intentions. You cannot opt out of gravity, cannot create a gravitational quiet zone, cannot build a cage that keeps gravitational fields at bay. This impossibility, we've discovered, is not a temporary technological limitation, but a fundamental feature of the universe, as basic as the 3 dimensions of space or the forward flow of time. The reason, as we've explored with patience and wonder, lies in the fundamental nature of the sources of these fields. Electric charge comes in positive and negative varieties that can cancel each other out, creating the possibility of neutral regions where electric fields vanish. But mass comes only in one variety, the kind that attracts, that creates inward-pointing field lines, that adds up rather than cancels out. This asymmetry is encoded in the mathematics of Gauss's law, confirmed by centuries of experiments, explained by Einstein's recognition that gravity is the curvature of space-time itself. Think one more time about those field lines we've been imagining throughout our journey. Electric field lines that can begin on positive charges and end on negative ones, creating closed loops within conductors, cancelling out to create shielded regions. Gravitational field lines that all point inward toward masses, never outward, never forming loops, never cancelling, always adding their contributions to the universal gravitational field. These invisible lines, these mathematical constructs that represent something real about the forces that shape our world, they tell the story of why some forces can be escaped and others cannot. And what a story it is. A story that reaches from the quantum realm, where virtual particles carry forces between bits of matter, to the cosmic scale where gravitational waves from colliding black holes ripple through the fabric of space itself. A story that includes Faraday in his metal room, discovering electromagnetic shielding, Cavendish with his delicate apparatus measuring the gravitational attraction between lead spheres, Einstein reimagining gravity not as a force but as geometry, modern scientists detecting gravitational waves that have travelled billions of light years to stretch and squeeze our detectors by less than the width of a proton. It's a story that includes you, right now, a conscious arrangement of atoms capable of understanding these invisible forces, of appreciating the difference between what can be shielded and what cannot, of grasping through mathematics and imagination truths about the universe that your senses alone could never reveal. You are matter that has organized itself to understand matter, mass that contemplates mass, a gravitational being achieving gravitational awareness. As you prepare to drift off to sleep, to enter that state where consciousness releases its grip and dreams take over, the gravitational field continues its patient work. It holds you to your bed, keeps the air pressed down around you so you can breathe, maintains the Earth in its orbit around the Sun, keeps the Sun in its path around the galactic center. While you sleep, gravitational waves from distant cosmic events will pass through you, stretching and squeezing space itself by amounts too small to notice, but absolutely real. The moon will pull on you, raising microscopic tides in your body just as it raises tides in the ocean. Every star you saw tonight, every star you didn't see, every bit of matter in the universe will continue to pull on you with forces that decrease with distance, but never truly reach zero. This is the universe you inhabit, not a collection of separate, isolated objects, but a vast web of gravitational relationships, an interconnected whole where every part influences every other part, where true isolation is impossible because gravity cannot be shielded. You are not in the universe, you are part of it, woven into its gravitational fabric, contributing your small but real influence to the cosmic gravitational field while being influenced by every other mass that exists. The electromagnetic fields around you will change through the night. Devices will turn on and off, signals will come and go, the electromagnetic weather will shift and change. But gravity will remain constant, patient, reliable. The pull you feel now will be the same when you wake, the same tomorrow, the same next year. This constancy in the midst of change, this reliability in a universe of flux, there's something deeply comforting about it. Whatever else changes, gravity remains, holding everything together, keeping the cosmic dance organized and predictable. And perhaps this is why we cannot shield gravity, because it's the force that provides continuity, stability, structure to a universe that would otherwise fly apart into cold, disconnected fragments. Without gravity's unshieldable universal attraction, matter would never have clumped into stars, stars would never have formed galaxies, galaxies would never have created the conditions for planets, and planets would never have provided homes for life. We exist because gravity cannot be shielded, because this force reaches through everything to pull matter together, to create the conditions necessary for complexity and consciousness to arise. In your dreams tonight, you might fly, might float free of gravity's bonds, might experience the weightlessness that your waking body can never truly achieve while remaining on Earth. These dreams of gravitational freedom are perhaps the mind's way of imagining what cannot be, of exploring possibilities that physics forbids, of experiencing in imagination what reality doesn't allow. But even these dreams are defined by gravity. They're meaningful precisely because they represent escape from something inescapable, freedom from something that always binds us. When you wake tomorrow, gravity will still be there, patient and unchanging, ready to shape another day of your gravitationally bound existence. You'll stand against it, walk despite it, lift things in opposition to it. Your heart will pump blood upward against it. Your muscles will work to maintain posture despite it. Your bones will bear your weight because of it. Every action you take will be in negotiation with gravity, this force you cannot shield, cannot escape, cannot turn off even for a moment. But now you know why. Now you understand that this isn't a limitation to be overcome, but a fundamental feature of the universe, as essential to reality as space and time themselves. The impossibility of gravitational shielding isn't a problem to be solved, but a truth to be accepted, even embraced. It's what makes us part of something larger, what connects us to the cosmos, what ensures that we're never truly alone in the universe, because we're always gravitationally connected to everything else that exists. The gentle pull you feel right now, that subtle pressure of your body against whatever surface supports you, that's your proof of membership in the cosmic community. You belong here, in this universe, connected to every star and planet, every galaxy and cluster, every mote of dust drifting in interstellar space. Gravity says you matter, literally. Your mass contributes to the universal gravitational field. You bend space-time. You pull on distant galaxies just as they pull on you. You're not a separate observer of the universe. but an integral part of its gravitational structure. As consciousness begins to fade, as the boundaries between waking and sleeping start to blur, the questions we've explored tonight can release their hold on your active mind. You don't need to remember every detail, every equation, every experimental result. The essential truth is simple enough to carry into sleep. We live in a universe where some forces can be shielded and others cannot, where some connections can be severed and others are permanent, where electromagnetic fields can be controlled. But gravitational fields simply are unchangeable and unshieldable, connecting everything to everything else in an eternal cosmic embrace. Let this knowledge settle into that deep place where understanding lives not as facts to be recalled, but as wisdom to be felt. The universe has structure, has rules, has deep mathematical beauty that we've only begun to understand. The fact that you can contemplate these rules, can appreciate this beauty, can wonder about forces you cannot see and fields you cannot touch. This itself is a kind of miracle, a gift of consciousness in a universe that seems, against all odds, to be comprehensible to minds like ours. The gravitational waves passing through you right now have travelled billions of years to reach you, carrying information about cosmic events that happened before Earth existed. The electromagnetic signals from your devices will fade and dissipate, blocked by walls and absorbed by matter, but the gravitational connection between you and the cosmos is eternal, unblockable, unbreakable. You are held by forces that have operated since the beginning of time and will continue until time itself ends. In this final moment of our journey together, as you prepare to release consciousness and drift into sleep, remember that you're not falling asleep in empty space, but in a rich tapestry of fields and forces, most of which you cannot perceive directly, but all of which shape your existence. The electromagnetic fields that you can shield, that human technology has learned to control and direct, and the gravitational field that you cannot shield, that holds you safe and secure, that connects you to everything else, that makes you a permanent participant in the cosmic story. Tomorrow the sun will rise, held in its course by the same gravity that holds you to your bed. The moon will continue its orbit, the planets their paths, the galaxy its slow rotation. And you will wake still embedded in the gravitational field that permeates all of space, still unable to shield yourself from it, still connected to every mass in the universe. But now you know why. Now you understand the deep physics and beautiful mathematics that make gravitational shielding impossible. This knowledge, this understanding, it changes nothing about gravity itself, but perhaps everything about how you experience it. So rest now in gravity's patient embrace, knowing that you cannot escape it, but also that you would not want to, for escaping gravity would mean escaping the universe itself, severing the connections that make you part of the cosmic whole. Let the last conscious thought be one of peaceful acceptance, of gentle wonder at a universe strange enough to have forces that can be shielded and forces that cannot, complex enough to create beings capable of understanding this difference, beautiful enough to make the journey of understanding worthwhile. The question we began with has been answered not with a solution that lets us shield gravity, but with an understanding of why we cannot and what this means. Electric fields can be shielded because charge comes in opposites that cancel. Gravitational fields cannot be shielded because mass only attracts, never repels. This simple asymmetry shapes everything from atoms to galaxies, from technology to dreams, from the evolution of life to the structure of spacetime itself. And as you drift into sleep, you remain part of this quiet universe, wrapped in its laws, carried by its mysteries, held by the one force you cannot escape, connected through gravity to every star above and every grain of sand below, gently, peacefully, inevitably, into the night where dreams of flying await, where consciousness releases its grip but gravity never does, where you rest in the embrace of the universe itself, unshielded and unshieldable, exactly where you belong.